So, good morning. Welcome to Krishna's classroom. In this talk, we explore one of the important concepts that appear toward the length and breadth of the measure and integration, namely some property valid almost W, which is abbreviated by the notation A dot. Now, what does this mean? This is what we are going to explore, and some consequences. Now, you recall our discussions on Riemann integration. We found that Riemann integration is generally valid for bounded real valued functions on bounded. I mean, that's where we. Then we found that all continuous functions are Riemann integrated. Then, of course, the question came, suppose the function has some discontinuities. And we found that if it's a finite set of discontinuities, then it is still Riemann integral. Further, you ask the question how far you can go. Then we introduce a concept of null set. And the null set, if you carefully examine the definition of the null set, you will see that it is a set with outer measure 0. Okay. Compare the definitions. Now, what we have proved eventually is that f is Riemann integral if the set of discontinuities of the function form a null set or a set of outer measure 0. Now, having introduced the concept of measure, we try to get this idea, because suddenly there are questions like which Lebesgue integrable functions are Riemann integral, and how do the two integrals compare? All these questions are to be considered. Now, with this objective in mind, we now define the concept of some property valid almost. Okay, so let us define. For a measurable set E, we are in R, we say that a property holds almost everywhere. Almost everywhere, abbreviated as AE. If there exists a subset containing E, for which measure of E naught is equal to 0, and the property is valid for all that means in the complement of E naught in E, the property is valid, and the measure of E naught is equal to 0. Now these are the two things. Okay, right? So that means everywhere except on a set of measure 0, the particular property is valid. Then you say that property is satisfied almost everywhere. That is, everywhere except on a set of measure 0, the property is valid. For example, suppose f is a real valued function, find from on an interval AB, or we say that f is bounded almost everywhere on if if f is bounded everywhere except on a subset E naught of within E naught, measure of so this is one example. More precisely, consider the function f of x equal to 1 or q, and this is equal to infinity. Then f is takes the value one almost in bracket we make use of the fact that the measure of q being countable, this is equal to talking about Lebesgue measure. That is where it fails to be bounded. And if you want another example, you can talk about continuity. Okay. Once again, we assume that the function is continuous everywhere except on a set of measure 0. For example, if you take the function define f of x n for this one, where n belongs to z, the set of all integers. This is the interval n to n plus 1 and equal to equal to 0 for then has discontinued. For x belonging to z. And the set of all integers form a set of measure 0. So we shall say that f is continuous almost everywhere. Now that is the expression. Okay. Now one of the consequences of this is the Borel cantilever lemma. See, many places we are going to come across this particular property. So let us state the theorem. Be a countable collection of measurable sets for which k equal to 1 to infinity phi. Then almost all x belonging to R belong to or at most finitely many of these, which means this property that almost all x belong to R means what? There could be a subset of measure 0 about which we are not worried about. Almost all x belong to R belong to at most finitely many of the case. Okay, right? So this is the one of the quick expression of the same idea. So let us do that. Work on it. Work out the proof. For each n by the countable subadditivity of the measure m, we have m of and from the given data this is less than, this is finite and this is finite from the given conditions. Now what we do is the following. We make use of the continuity of the measure, which we have discussed earlier. Now what we do is we take these sets. So if you want, you can call the following, that E. So let us use the notation. Union K to N to E K. Then what do we have? Then we have that AN is interest. So AN is a, what you call, decreasing. Therefore, you have, now you take this one, measure of, this is what we have used, this is equal to measure of N. Okay, and that by the continuity of measure, we have, this is equal to limit n tending to infinity measure of, and this is of course is less than or equal to limit n tending to infinity. What is an? An is union k equal to n to infinity ek. Yeah. And that is less than or equal to k equal to n to infinity measure of, I think so. Sorry. Measure of that is an omission, sorry. But here we use subaddition. And this, you know, what you have here? You have assumed that sigma k equal to 1 to m of k is finite, and therefore the limit of this as n tends to infinity is 0. Okay. So this follows from the given condition. Therefore, for almost all x are fail to belong to intersection n equal to 1 union k equal to n to okay. Because this is what we have seen. Measure of this class is equal to 0. What does it mean? Means almost all x fail to be inside x. Okay? It's a set of measure 0 in which there may be some x's. Okay? But that exactly is a set of measure 0. Therefore, almost all x fail to satisfy this particular property. Now let us examine the meaning of this. That in turn belong to most finitely many now you can see that if the failure of this would mean that measure of that class is not equal to 0 and this condition would fail. Measure of this equal to 0 would fail. Okay, so that is something which you can easily see. Okay. Right, so that proves this result, which is may be useful or just give some indication of how things happen. It says almost all x belong to R belong to at most finitely many cases. Okay. That means it cannot be belonging to infinitely many cases. Okay. Right. So one of the exercises that you can try out is construct an example with this properties. Okay. So now we look at further properties of, continue with the properties of it. So we call, so this completes the call the following properties. Possessed by the Lebesgue outer measure Now, why do we recall these properties? The reason is this. You see that the space of all or the set of all Lebesgue measurable functions script m is contained in the power set of R. In fact, M star is defined for that is every element of power set of, okay. So M is defined on a subcollection of that. M is defined on a of PR, namely M. Now what we have is that M and M star coincide on script M. The set function defined on. See, M star is defined, is a set function defined from including infinity, and M is defined from script M the this is okay. Okay. So let us see which are the properties that are inherited by M. Now the first property is that finite additivity. Now you know that M star is finite additive. And so is naturally M is so finite additivity is something that is inherited from M star. Second property is for any finite disjoint collection K we have M of equal to this is what second problem. Another property that is inherited is what you call the monotonicity, because you know that A is contained in B. Okay, so we will write down if A is P. Hence, so that is also another property that is inherited. Third property that is inherited is the excision. So what you can prove is this: if A comma B belongs to M and measure of A is finite, then comma A is contained in B, measure of this is a property that is inherited for the from the this one. Okay. Hence, measure of B equal to measure of B slash A equal to 0 implies or I will put it this way. Implies measure of E slash A this is the situation, the scenario that you have is so the situation is this. This is B. Okay. So if measure of A equal to 0, then measure of B slash A, whatever is left out, This is V slash is equal to the measure of the fourth property, countable monotonicity. This is of course a fusion of the two properties, the monotonicity and the countable additivity. What it says is this: for any countable collection of elements Ek of M such that we have M of Ek is less than or equal to sigma Now you see that this is essentially, the measure of this is less than or equal to this one. Okay. Therefore, measure of E is less than or equal to, that is measure of E because this is measurable. This countable collection is measurable, and this is by subadditivity. This is less than or equal to so this is essentially a fusion of two things, namely the what you call monotonicity and countable subadditivity. We shall make just with that as a remark. So we make some remarks. Countable monotonicity is an amalgamation of monotonicity and countable In fact, it's valid for NISER also. Okay. Second remark is that we shall later accountable monotonicity plays a crucial role measure gives a distinct edge for Lebesgue integral over Riemann integral. In fact, we shall comment about this later. Okay. And this is something that we would like to. Now I think we just recall one of the results. Possibly we have proved it already. I don't know, I am not even sure. But let us recall this. Now we are trying to venture or ask a deeper question. So the next question that we are asking is this. Non-measurable that is M a proper subcollection of proper subcollection of this is the question. That's the one that we are now taking. So this needs some work. It is not obvious that there are non-measurable subsets. It's not a simple thing to provide you with an example of a non-measurable set. One has to construct one. The construction is rather intricate. Okay. But before that, let us recall the following. Recall that if the outer measure of a of an element of a subset of R is 0, then it is measured. That is, if m star of E equal to 0, that is m star of E equal to 0 implies E belongs to the measured class, and measure of one of the consequences of this result. So we will prove this, give a quick proof of this. So let us, because it's an important result, this m star of lies what do we have to prove? We have to prove this. For any A, R, you have to prove this. That is, m star of A equal to m star of now see clearly that implies we need prove that m star of E equal to 0 implies what? Implies is greater than or equal to but this is obvious. Why it is obvious? But this is obvious. Why it is obvious? Because observe that hence what about the other one? A intersection E complement is less than or equal to m star of E. Therefore, what do you get? You get m star of A intersection E plus M star of complement. This is equal to M star of, and this is less than or equal. Okay. Now this is exactly what we wanted to see. This is this thing. Okay. Hence, E is measurable and M star of E or M of E equal to zero. So that is what we have proved. And one of the consequences is that it's an important consequence. The corollary this is obvious. Why? Because if E1, then we have M star of equal to 0. Okay. It's a set of that implies by the previous theorem and that completes the discussion. Okay. So I think we will complete the discussion today, and what we are now going to ask is, does there exist non-measurable subsets? Second question that we would like to ask is a question similar to this. Suppose a set E is measurable. Is it possible to assert that every subset of E is also measurable? Okay. Now these two questions we shall explore. So the questions that we explore are, is that is one question. If E is with a non-zero measure is every these are the two questions that we try to address in our next lecture. Okay. And it says that if the measure of E is 0, then all subsets of E are measurable. So we have to resolve only for the case where measure of E is not equal to 0. That means measure of E is positive. Then we would like to investigate whether all the subsets of E are measurable. Okay. That depends on the first place we are able to prove that every subset of R is measurable, then all questions are closed at that stage. If not, what happens? Okay. There is some subset. Suppose that we prove that there is some subset which is not measurable. Then you see that if R is measurable, since R is measurable, we cannot have, the consequence is that we cannot have, there exists some subset of R which is not measurable. Therefore, the second question is answered. But the question is it true for every measurable subset with non-zero measure? That is, we are asking a deeper question. That means, given a subset which is measurable and having a non-zero measure, is it always possible to assert that there is a subset which is not measurable? Now, these are some of the questions that we like to explore, and that in a way would complete our discussion on what are called, all the questions that naturally come up in the context of what is called a navigation. So thank you very much. We'll stop here.